Hello, in this lecture we'll talk about the limit of a sequence. A sequence is a set of numbers, and a sequence can be finite, like the sequence 1, 5, 7 has 3 terms. So it is a finite sequence, but the sequence that we are talking in this lecture are all infinite sequences. That is to say, the terms in each sequence are infinite terms, like the natural numbers. The natural numbers consist of infinite terms. That is to say, it is 1, 2, 3, 4, 5, 6, 7, n. So we are talking about the limit of infinite sequences. Okay, and we actually want to find out the limit of an infinite sequence. And what is the limit, the definition of the limit of a sequence? The limit of a sequence is the value that the terms of the sequence tend to, and is often denoted using the lim symbol. Like lim is abbreviation for limit, the limit of sequence an when n tends to infinity. Here the limit of the infinite sequence an when n tends to infinity. So if such limit exists, that is to say, the limit of sequence an when n tends to infinity is equals to L, then this sequence an is convergent sequence. Okay, this sequence an, that its limit is L, is defined as convergent sequence. Okay, it is a convergent sequence. And if the limit doesn't exist, then the sequence is divergent. Okay, so if we have sequence Bn that doesn't have a limit, then it is defined as divergent sequence. If a sequence has a limit, then it will have only one limit. That is to say, if we have sequence that has 2 limits, then that sequence doesn't have limit at all, because of the fact that any sequence with a limit will have only one limit and one limit only. Okay, so if the limit of sequence an is equals to L, then it is equals to L and not to any other limit. Okay, So actually the limit of a sequence is said to be the fundamental notion on which the whole of mathematical analysis ultimately rests. So actually a number L is the limit of the sequence AN when n goes from 1 to infinity, if the numbers of the sequence AN become closer and closer to L. So when n increases, then the numbers of the sequence get closer and closer to the limit L. Okay? So, what is the definition of the limit of a sequence? Actually, we call L is the limit of the sequence AN. L, the real number L, is the limit of the sequence AN when n goes from 1 to infinity, and we will write down that the sequence AN, the limit of the sequence AN is equals to L. Okay, so this means that the limit of sequence AN is equal to L when n goes from 1 to infinity. And the second way to write down that the limit of sequence AN is equals to L is lim, that is the abbreviation for limit of sequence AN when n tends to infinity is equals to L. Okay? So those are the two ways to write down that the limit of sequence AN is equals to L when n tends to infinity. Either you will write down that the sequence AN with the arrow is L, and the second way to write down that the limit of sequence AN when n tends to infinity is L is lim AN, and when n tends to infinity is equals to L. Okay, so actually the limit of sequence AN is equal to L only and only if the following condition holds. I'll repeat again, the limit of sequence AN when n goes from 1 to infinity or when n tends to infinity is L only if the following condition holds. The condition is that for each real number epsilon that is greater than 0, there exists a natural number capital N such that for every natural number n that is greater than capital N, we will get that the absolute value of an minus the limit L is less than epsilon. And epsilon is usually very small number, very small positive number. Okay, so if you give me epsilon that is a small positive number, then if sequence an has the limit of L when n tends to infinity, if the limit of sequence an is L, then it means that for each epsilon that you will give me that is a positive number, I can find n that is a natural number, and for every n that is greater than capital N, we'll get that an minus L, that is the limit of the sequence an, the absolute value of an minus L is less than epsilon. Okay? So only if this condition holds, we can write down that the limit of sequence an when n tends to infinity equals to L. Otherwise, sequence an will not have any limit if this condition doesn't hold. Okay, so actually the terms of the sequence are close to the limit up to epsilon. That is to say, if the limit of sequence an is A, then the radius of the environment of A is epsilon. That is to say, this point is A minus epsilon, and this point is A plus epsilon. And whenever a sequence has a limit that is equal to A, it means that most of the terms of the sequence must be located inside these brackets, from A minus epsilon until A plus epsilon, no matter how small epsilon is. Most of the terms of the sequence an that the limit of its sequence is A must be located inside these brackets. So epsilon here is the radius of the environment A. Okay? And because of the fact that until capital N there is a fixed terms, until capital N there will be a fixed terms of the sequence an, and from n until infinity we will have infinite terms of sequence an, and they are all will be inside these brackets. That is to say, we have infinite terms of the sequence AN that are all located in the environment of A, that is the limit of the sequence AN. Okay? Or here, the limit here of the sequence AN, it is actually L, or we can say that the limit is A. So here I wrote down that the limit of sequence AN is L, so I write down that the limit is L. And here, this point we have L minus epsilon, and at this point we will have L plus epsilon. So most infinite terms of the sequence AN are located inside these brackets from L minus epsilon until L plus epsilon, and the radius of this environment of the limit L is epsilon. Okay, I repeat again. Until capital N, there is a fixed number of terms that are not located inside these brackets, but infinite terms of sequence AN are located inside these brackets. That is to say, infinite terms of sequence AN are located inside the environment of L. This is the environment of L. Environment of the limit L, and infinite numbers of terms of the sequence AN must be located inside the environment of L in order that sequence AN will have the limit of L. And only fixed number of terms will be located outside of this environment of those two brackets of the limit L. Okay? And epsilon could be any small positive number as we would like. Okay? So you can give me the epsilon, that is very small positive number, and I will have to find out capital N that belongs to the capital N that belongs to the natural numbers, and from capital N onwards all the terms of sequence AL will be located inside those two brackets. That is to say, we have infinite members of terms AN that are all located inside the environment of L. That is to say, inside those two brackets from L minus epsilon until L plus epsilon. That is the condition that must hold in order that the limit of sequence AN when n tends to infinity will be equal to L. Only and only if this condition holds, we can say that the limit of sequence AN when n tends to infinity is equal to L. Otherwise, the sequence AL will not have a limit. Okay, so for any epsilon that you will give me that is a positive number, I will have to find out n that is big enough, a natural number, capital N that is big enough that from n onwards all the terms will be located inside these two brackets. That is to say, most of the terms of the sequence AN will be located in the vicinity of L, or in the environment of the limit L. Actually, infinite numbers of terms of the sequence AL must be located inside those two brackets, that is the environment of the limit L. Okay, so only if this condition holds, we can write down that the limit of sequence an when n tends to infinity is equals to L. Here L is any real number. I'm writing down that L is any real number. So actually, symbolically, we can write down that the sequence an, the limit of the sequence an when n tends to infinity will be equal to L only if we can find out any positive epsilon, that is to say it is greater than 0, and for any epsilon that I will give you, in order to that the limit an, that the sequence an will have a limit that is L, then for any epsilon that is a positive number that I will give you, you must find out capital N, that is a natural number, that is to say it belongs to the natural numbers, and for any n that also belongs to the natural numbers, we will get, for any n that belongs to natural numbers and the natural number n is greater than capital N, that is also a natural number. So for every n that is greater than capital N, we will get that n is the index of the theorem, and an is the theorem itself. So an, that is to say, when n is greater than capital N, then the theorem of the sequence is A of this n minus the limit that is L, the absolute value of an minus L will be smaller than the epsilon that I gave you. Okay, so for any epsilon as small as you would like, in order that the sequence an will have the limit L, I will have to find out capital N that belongs to the natural number in such a way that for any n that belongs also to the natural numbers, so for any n that is greater than n, for any n that is greater than capital N, you will get that the absolute value of an minus the limit L will be less than epsilon. Okay? So only if this condition holds, we can write down that the limit of sequence an when n tends to infinity is equals to L, and L is any real number. N is any real number. Okay. So if sequence AN converges to some limit, that is to say to limit L, then it is convergent sequence. Then we can say about sequence AN that is convergent sequence. Okay, if sequence AN when n tends to infinity converges to L, we can say that sequence AN is a convergent sequence. Otherwise, if sequence Bn when n tends to infinity doesn't converge, then we can say that sequence Bn is divergent. Okay, this sequence Bn that doesn't converge will be defined as divergent sequence. So we finished to talk about the finite limits. I'll repeat again that sequence AN when n tends to infinite will have the limit L only and only if we can find out, only and only if for any epsilon that is a small positive number, we can find out capital N that belongs to the natural numbers, and for any n that is also a natural number that is greater than capital N, we will get that the absolute value of AN minus the limit L is less than epsilon. Only if this condition holds, we can say that the limit of sequence AN when n tends to infinity is equals to L. Otherwise, if this condition doesn't hold, sequence AN doesn't have a limit, and we can say about sequence AN that is a divergent sequence. And if sequence AN has the limit of L, we can say about sequence AN that is convergent sequence. Okay, so finish to talk about finite limits. In the next step, I will talk about infinite limits. Okay. So actually, sequence AN when n tends to infinity can have a limit that is any real number, but it is also can have a limit in the broadest sense that is equals to plus infinity. Like the natural numbers, we know that the limit of the natural numbers, that is to say, the limit of the natural numbers that has infinite terms, consists infinite terms that are 1, 2, 3, 4, 5 until n. Until n, the limit of these natural numbers is equals to plus infinity. Okay, so the natural numbers have a limit in the broadest sense at the limit of the natural numbers, that is to say the numbers 1, 2, 3 until n, the limit is plus infinite. Okay? So we can say that the limit of sequence an when n tends to infinity will be equal to plus infinite only if the following condition holds. The condition is that for every real number k, there is a natural number capital N, such that for every natural number n that is greater than capital N, we will get that an is greater than k. That is to say, the sequence terms are eventually larger than any fixed k. So actually, for any k as large as we want, if sequence an when n tends to infinity equals to plus infinite, then the following condition must hold. The condition is that for any k as large as we want, we can find out capital N that belongs to the natural numbers, and from capital N onwards, all the terms of sequence an will be greater than k, and k will be could be any large number as we want. So if for any k as large as we want, we can find out capital N that belongs to the natural numbers, and from capital N onwards, all the terms of the sequence, that is to say from any n that is greater than capital N, that is to say from capital N onwards, all the terms of the sequence an are greater than k. Okay, so only if this condition holds, we can say that the limit of sequence an when n tends to infinity will be equal to plus infinite. Only and only if this condition holds. I'll repeat again on the condition. For any large number k, or for any k as large as we want, we can find out capital N that belongs to the natural numbers, and from capital N onwards, all the terms of the sequence will be greater than k. Okay? So only if this condition holds, we can say that the limit of sequence an when n tends to infinity will be equal to plus infinite. Okay? So actually we can write down here symbolically. It can be written in this way. For any k as large as we want, for any k, this is the sign of for any k as large as we want, and k belongs to the real numbers. So for any k, there is capital N that belongs to the natural numbers, and from capital N onwards, all the terms of the sequence will be greater than k. That is to say, for any n that is greater than capital N, that is to say, for all the indexes that are greater than capital N, then the value of the terms of the sequence, that is to say, an, will be greater than k, that could be any large number as we want. So only if this condition holds, that is to say, for any k that is as large as we want, that belongs to the real numbers, we can find a capital N that belongs to the natural numbers, and from capital N onwards, all the terms of the sequence an will be greater than that k. Okay? So only if this condition holds, we can say that the limit of sequence an, when n tends to infinite, is equals to plus infinity. Only and only if this condition holds. The limit of sequence an when n tends to infinity will be equal to plus infinity. Okay? Repeat again. For any k as large as we want, k belongs to the real numbers, we can find out capital N that belongs to the natural numbers, and from that index, that is capital N onwards, all the numbers of sequence an will be greater than k. Okay? From the index of capital N onwards, all the terms of the sequence will be greater than k. Only if this condition holds, then the limit of sequence an when n tends to infinity will be equals to plus infinity. Okay? And likewise, we can define the limit of a sequence will be equal to minus infinity when n tends to infinite. That is to say, similarly, we say that a sequence tends to minus infinity so sequence an and n tends to infinite, so the limit of this sequence will be equal to minus infinity only and only if the following condition holds. For every real number k, as small as we wish, as small as we want, there is a natural number n belongs to the natural numbers, such that for any natural number n that is greater than capital N, that is to say, all the terms of the sequence an from the index capital N onwards, that is to say, for every natural number n that is greater than capital N, or for all the terms that are greater than capital N. Capital N is the index of the term, and an is the value of the term. So for every n that is greater than capital N, we'll get that an, the value of the term, will be less than k. And I will remind you that k could be as small as we wish. So, by this way we proved that the terms of sequence an are smaller than any small number k. Therefore, the limit of this sequence an is equals to minus infinity. Okay, so actually symbolically we can write down that for any k, this is the sign for any k, for any k as small as we want, and k belongs to the real numbers, we can find out there exists capital N that belongs to the natural numbers, so from the index capital N onwards, all the terms of the sequence an will be smaller than k. That is to say, for every n that belongs to the natural numbers, there will be n that is greater than capital N. That is to say, from the index capital N onwards, all the terms of the sequence an will be smaller than k. Okay, in this way we actually proved that the terms of sequence an are smaller than any small number k. Therefore, the terms of sequence an, when n tends to infinite, are approaching to minus infinity, or the limit of sequence an when n tends to infinity is equals to minus infinity. Okay? So, in the next step, I will present to you an example I will repeat again on the definition of a finite limit. A sequence AN converges to a real number L if for every epsilon that is greater than 0 there exists and capital N that belongs to the natural numbers, such that whenever N is greater than capital N, it follows that the absolute value of AN minus the limit L is smaller than epsilon. So that is the definition of a limit of a sequence. So only if this condition holds, sequence AL will have the limit of L. Otherwise, sequence AL will not have any limit. So that is the definition of a finite limit. So sequence AN will have the limit, the finite limit L. Here L is a real number, any real number. That is to say, it belongs to capital R. So sequence AN converges to a real number L if for every epsilon that is greater than 0 there exists capital N that belongs to the natural numbers, such that whenever N that is greater than capital N, that is to say, from the index capital N onwards, all the members of the sequence AN actually will be the absolute value of AN minus L from the index capital N onwards. All the members of the sequence AN, the absolute value of AN minus the limit L will be smaller than epsilon. Okay, in the next step I will give you an example how we can implement the new rule in order to find out the limit of the following sequence. So actually we have here we have to prove that the limit of the sequence 1 over n when n tends to infinity is equals to 0. First of all, intuitively, the terms of this sequence AN is equal to 1 over n, the first member is when n equals to 1, it is 1 over 1. The second member is when n equals to 2, it is 1 over 2. The third member is when n equals to 3, that is 1 over 3. And the 100th member will be when n equals to 100 is 1 over 100, etc. until 1 over n. So you can see from this the sequence an tends to 0. As n increases, the terms of the sequence decrease towards 0. Okay, from 1 we have here 1, 1/2, 1/3, 1 over 100. So you can see that the terms of the sequence tends to 0 whenever n increases. Therefore, intuitively we can say that the limit of this sequence when n tends to infinity equals to 0. But we have to prove, according to the definition of the limit of a sequence, that indeed the limit of this sequence 1 over n is indeed, when n tends to infinity, is indeed equals to 0. So here let epsilon that is greater than 0 and capital N that belongs to the natural numbers so with n that is greater enough, with capital N that is greater enough, there will be small n that is greater than capital N, in order that the limit of sequence an that is equal to 1 over n will be equal to 0. The following condition must hold, that for every positive epsilon we can find out n, capital N, that is big enough, and for every n that is greater than capital N, we will get that the absolute value of 1 over n minus 0 is less than epsilon. Okay? So actually, in order that the limit of this sequence will be equal to 0, the following condition must hold. That for every epsilon that is greater than 0, we can find out capital N that is big enough, and for every n that is greater than capital N, that is to say from capital N onwards, all the terms of this sequence an equals to 1 over n. So if we subtract the term, the absolute value of the term of the sequence minus the limit that is 0, the absolute value of 1 over n minus the limit that is 0 will be less than epsilon. So this condition must hold in order that the limit of this sequence an equals to 1 over n when n tends to infinity will be equal to 0. Okay, so we will prove that we can find out the appropriate capital N that holds this condition. that the absolute value of 1 over n minus 0 is smaller than epsilon. Actually, 0 change nothing, so we can cancel here 0, and here we will get that the absolute value of 1 over n must be less than epsilon. And because of the fact that n belongs to the natural numbers, then 1 over n must be a positive number. And the absolute value of any positive number is the positive number itself. The absolute value of 5 is 5. So we can cancel out the absolute value, because the absolute value of 1 over n is 1 over n. Okay, the absolute value of any positive number is a positive number. So we will get here, so we cancel out the absolute value, and we get that 1 over n is less than epsilon. Okay, 1 over n is, so we have the inequality that 1 over n is less than epsilon. Okay. So here we will multiply this inequality by n, and we will get that 1 is smaller than n times epsilon, and here we will divide this inequality by epsilon. Epsilon is a positive number, so it is allowable to divide this inequality by epsilon, and we will get that n is greater than 1 over epsilon. Okay? So we'll choose capital N. So in order that this condition will be correct, that the absolute value of 1 over n minus 0 is less than epsilon, we will choose capital N that is greater than 1 over epsilon. Okay? And we know that we have to choose n that is greater than capital N. That is to say, from the index that is greater than capital N, all the terms of the sequence must give us that the absolute value of 1 over n minus 0 is less than epsilon. So we have to choose n that is greater than capital N. So here we will divide this inequality by n, and we will get that 1 is greater than capital N over n. Here we will divide this inequality by capital N, and we will get that 1 over capital N is greater than 1 over n. So actually, we have already found out that the absolute value of 1 over n minus 0 is equals to 1 over n, the absolute value of 1 over n, and is equals to 1 over n. And we know that n is greater than 1 over epsilon. So if we substitute the denominator n by 1 over epsilon, we will get that, so actually 1 over epsilon is less than n. So when we make the denominator smaller, then the number itself will be greater. That is to say, 1 over n will be less than 1 over capital N. Again, we know that n is bigger than capital N. So we substituted n by capital N. So we made the denominator smaller, and therefore the number itself will be greater. The number 1 over n will be greater than 1 over n, because n is smaller than capital N is smaller than n. Therefore, when you made the denominator smaller, then the number itself must be greater than 1 over n. So again, n is smaller, capital N is smaller than n. Therefore, 1 over capital N must be greater than 1 over n. And we also know that capital N is greater than 1 over epsilon. So if we put in the denominator instead of capital R N 1 over epsilon, so we decrease the denominator, therefore the number itself will be greater. So 1 over epsilon will be greater than 1 over capital N. Why? Because 1 over n is smaller than capital N. So whenever you make the denominator smaller, then the number itself will be greater than 1 over capital N. 1 over epsilon is smaller than capital N, therefore 1 over epsilon will be greater than capital N, because whenever you make the denominator smaller, then the number itself must be greater than 1 over capital N. So, and 1 over epsilon is epsilon. So actually proved that for every epsilon that is greater than 0, there exists n, capital N, and for every n that is greater than capital N, we get that the absolute value of 1 over n minus 0, that is the limit of the sequence, is less than epsilon. So we actually proved that for any epsilon that is a positive number, there exists a natural number capital N, so that from capital N onwards, every term of the sequence after capital N, that is to say from capital N onwards, all the terms of the sequence, if we subtract the absolute value of any term minus the limit that is 0, will be smaller than epsilon. Therefore, 0 is the limit of the sequence 1 over n, when n goes from 1 to infinity. Again, the limit of sequence 1 over n when n goes from 1 to plus infinity is equals to 0. We actually proved it according to the definition of a limit of a sequence. For every epsilon that is a positive, you can find out n, capital N, and for every n that is greater than capital N, that is to say from capital N onwards, the absolute value of 1 over n minus the limit that is 0 will be less than epsilon. Therefore, the limit of the sequence 1 over n when n goes from 1 to infinity is equals to 0. Okay? Okay, thank you very much.